Hello, everyone, again. Let's keep talking about the textbook from Halliday and Resnick, the 10th edition, chapter 29. In this particular instance, we'll go to chapter 29, which talks about magnetic fields due to currents. We're going to talk about the Biot-Savart law, which is very important. And like I said, let me write it down, actually. Let me actually point out to what this is. This is the law of Biot and Savart. I'm sure that my pronunciation is less than perfect here, guys, but so this is it. The law of Biot and Savart says, it's essentially a law which is experimentally deduced, and it is an inverse square law. The differential B field associated with an element of current, an infinitesimal for our purposes, a very small infinitesimal, the element of a B field associated with an infinitesimally long segment carrying current, and what that does at a particular point away from the current, what kind of B field is produced at that point, pertains to the law of Biot and Savart. The law, which is experimentally deduced, is an inverse square law. Further away you get, the less B field is associated with what is going on with the current flowing. The further away you go, the less B field is associated with it, related to the square of a particular distance. Now, it's more complicated. It's a slightly more complicated matter than this, but essentially, based on what I said earlier, maybe it's easier if we look at a couple things first. If there was current flowing this way on an infinitely long, for example, on an infinitely long segment of wire, or an infinitely long wire carrying current I right here, carrying current I, what is the B field here? Well, if the current, and this is basically Biot and Savart's law, the infinitesimal B field at a point P, in this case here. Now look, this is very important. This wire can be curved in any way that one would wish to see the wire curved. The wire can be curved in practically an infinite number of ways, and hopefully there would be a way to reasonably and somewhat easily find out what's going on as far as a total B field associated with what is happening there. But this wire can be curved in any number of ways. We're making it kind of easy right here just to get a visualization of what's going on. What is dB vector? What is dB vector at the point P? Good question. What's dB vector at the point P? Well, dB vector at the point P is directly proportional to how much current is flowing. In what direction it's flowing, I guess that plays some kind of a role at some level, because there's a cross product in this Biot-Savart law. But certainly it's directly related to the amount of current that is passing through the wire. The more current, the more B field that would be taking place here. And over a small portion of wire, an infinitesimally small portion of wire, right here, let's say, let me maybe use a different, the portion of wire right here, let's say it was right here, just this portion right here, and that's ds. For that very, very small portion of wire, how much dB do we get? For associated with this ds vector, or distance, ds, I can put a vector symbol on there, this length of ds of wire with the current I flowing through it for this length, current I flowing through this thing is flowing throughout an infinitely long wire. Let's just take a snapshot of what's happening with the infinitely long wire over this short segment of length ds. What kind of dB vector would be taking place? What very small portion of B field, dB vector, is associated with the current I going through the wire at this point over a length ds? Well, certainly the more current that is going through the wire, the more B field that we're talking about. That's reasonable. The further away this infinitesimal element of wire with current I going through it, the further away that is from here, the less B field there's going to be, and the greater that I is, the more the B field is going to be. So it's directly, the dB vector is directly proportional to the amount of current and inversely proportional to the distance away. We'll talk more about this. There's much more to be said about this, which makes sense. The closer I brought the P, the closer I brought the point P, if I could move it, I could say another point P. If I brought it much, much closer, we're talking about a greater B field. It's closer to the flow of current equal to I. It's closer to it, and so that's pretty significant. Well, okay, there's more that goes in it. So what are we saying here? The differential B field is going to be directly proportional to the amount of current going through the infinitely long wire, and it's going to be inversely proportional to the distance away from the wire, roughly along those lines. Well, the law of Biot and Savart is telling us, well, we could set up a differential B field, and from there, if we do calculus correctly, we can find out what the total B field is for an infinitely long wire, or for an infinitely long wire going infinitely long in both directions, and the current I is flowing through it, or if we were to somewhat cut that infinitely long wire in half and just have a semi-infinitely long wire going in just not coming at us from both directions. The direction of the current is going to the direction of the current is the same from infinitely far away going to infinitely far away. It's just an infinitely long wire. If you were to cut it in half, it's reasonable to say it's going to be half the B field. So, and we'll see that indeed is the case. That, of course, is working with this simple situation of the wire with the current I, and it's a straight wire, and we can talk about a semi-infinitely long wire or an infinitely long wire. Yeah, we can certainly talk about all that. We also could talk about this thing being curved in many ways, and we could hopefully approximate, at the very least, mathematically be able to talk about how the curvature of the wire is taking place for us to do mathematics and for us to do calculus and be able to find the total B field. If maybe that doesn't lend itself too easily for it, maybe we can find a very, hopefully we believe we can find a very good approximation to what's going on. But this holds across the board, guys, when they do it. Well, this is all in the Halliday and Resnick book, and in practically any other textbook covering this material, you're going to see this covered and talked about. In the Halliday and Resnick book, 10th edition, in chapter 29 for magnetic fields due to currents, it's page 837. This is talked about. So it's experimentally deduced. It's an inverse square law. Mu 0 is a constant. 4 pi is a constant. It's directly proportional to I, and directly proportional to this product. Well, not necessarily, in a sense, I guess you could say. This is ds vector cross r vector. So it's directly proportional to this cross product. R vector is this length right here. So that entire going in this direction, that's R vector, its length is R. its length is r, and r vector just tells you what direction it's going at. R hat is just a unit vector pointing in the direction of r vector. So the size of r vector is r. It's all this. It's this hypotenuse with s right here, with, right here is from here to here is s, and from here to here is r. So here's r, here's s squared plus r squared. S squared plus capital R squared is equal to small r squared, and we can talk about how that all works out. So that's where this is coming from, guys. Kind of set up some of the arguments that are going on here, guys. The sine of theta equals the sine of 180 minus theta. Or if it's in radians, the sine of theta equals the sine of the quantity pi minus theta. And that's what this is said right here. And we can do that by looking at the unit circle. If this is length s, the yellow thing is length s, the blue thing is length capital R, the square root of the sum, s squared plus capital R squared, is the length of the hypotenuse, which is this right here, which is equal to that small r we were talking about. And that's the same as the quantity s squared plus capital R squared to the 1/2. Okay, so we talked about, so we can look at that as well, just to kind of have it in the back of our mind when we're doing this. If you do the cross product of the infinitesimal length, or let's, I can use that language, but maybe a better language is just saying, if I do the cross product associated with these two items, the differential length ds vector cross the quantity r vector, that cross product divided by r squared times the current, the magnitude of the current. So differential element ds vector cross the r vector. The differential element ds vector cross the vector that has magnitude, length of the hypotenuse, r, and we'll call it r, has that magnitude, and it goes the direction of r vector. R vector is as big as the hypotenuse that we were just talking about right here. Right here. And that's a constantly changing hypotenuse. If I had if I started down here, well, that's the angle theta. The angle theta down here is a 90-degree angle. If I brought this guy straight down here, the angle theta is a 90-degree angle. And then as you pick it up, the angle goes from 90 degrees to bigger than 90 degrees, on and on. Keep going, keep lifting this way. It goes from 90 degrees to 100 degrees to 110 degrees to 120 degrees. Keeps going. If you keep going, the thing eventually in the limit is going to go to 180 degrees. It's going to go from 90 degrees to 180 degrees. If I wanted to look what was going on the other side of this, it would be going from 90 degrees to 89 degrees to 70 degrees. On the other side of that, it'd be hooking down like this, and this guy right here would be going this way, coming down this way, and the angle under consideration would be going towards zero. So you're going from 0 to 180 degrees if you go from infinity, if you go from the low infinity, down here, infinitely far away, negative infinity, all the way to positive infinity, you're going, the angle, this angle right here, that angle right there, you guys, is going to be anywhere, it's going to be 0 to 180 degrees. Starting here, it's going to be 90 to 180 degrees. I tell you what, because of the symmetry of what's going on here, and the fact that the sine of theta is equal to the sine of the quantity 180 degrees minus theta, which is the same as the sine of theta is equal to the sine, if we're talking about radians, it's the sine of theta equals the sine of the quantity pi minus theta. For radians, degrees, same thing, just same argument, just different numbers here. So for radians, sine of theta equals the sine of the quantity pi minus theta. For degrees, sine of theta equals the sine of the quantity 180 degrees minus theta. True. We're not really worried about, the way this thing opens up. It's you got 90 degrees here, and it's going this way, and it's going to, if you take this line right here and line segment right here, you take this line segment right here, and you say, okay, well, let me just move it down here. That thing is 90, and it just keeps going to 180. Go the other way, it's going to go 89, 80, 70, down that way to 0. But when you're actually finding the distances involved, look, any triangle I draw up here, I can draw the exact same triangle down there, completely symmetric. And the angle under consideration is if one of them is, for example, if this theta right here is 120 degrees, I can, if this is 120 degrees, if this right here is 120 degrees, this is 60 degrees. I can make a 60 degree angle right here, down there, and the cross product, what is the cross product, you guys? The cross product is magnitude times the sine of the angle between them. The sine, if this is 120, the sine of 120 is the same as if you brought this in. Here's 120, here's 60. I can get, here's 120, here's 60. I can build this exact same triangle down here, and I got a 60 degree angle. Wait a minute. The sine of the 60 degree angle, sine of the 60 degree angle is the same as the sine of the 120 degree angle. So it's complete symmetry. What I find down there, I'm finding the exact same thing right here. What does that mean? Well, I can get an answer. Great. Now I got the answer. Now, if I did find that answer, if I cut that answer in half, I'd be finding the B field, the total B field associated with a semi-infinitely long wire, not an infinitely long wire. Another way to put it is, why don't you just find the B field associated with a semi-infinitely long wire, find that B field, and then double it, because you'll have the other bunch of triangles, all of them symmetric with all these, an infinite number of triangles, each one of them, each one of any one of them symmetric with another triangle down here. So you just double it when you're doing it. So they're basically saying, guys, the book's got a good presentation on it. Practically any book regarding these matters is going to have a decent presentation on it. But this is really the argument. dB vector equals mu 0 over 4 pi, that's a constant, times I going through the wire, times the cross product of the differential element ds vector cross r vector. Get an answer, divide that by r squared. That's it. That's Biot-Savart's law. And if I do the integration properly, I can find the B field at a particular point. Okay? And, there's some things I've done as far as some of the problems that are involved, you guys, from this particular chapter that I've gone through. Some of the assumptions that I've seen made, I don't know, they're not really that obvious, but I've solved it as though those assumptions were okay, and I'm sure that they are. Perhaps I'm just missing something, but you'll see that for problems 55 and 88 that'll scroll at the end of this video. Here, let me just talk about a very broad statement, Biot-Savart's law, dB vector equals mu 0 over 4 pi. dB vector equals mu 0 over 4 pi times the current I times the cross product of the differential element ds vector cross r vector, all of that divided by the magnitude of r vector squared. Okay, so that's Biot-Savart's law, guys. It's going to be useful to us. Let's take a look at it. We talked about some of the assumptions you can make. Let's say a couple things here, guys. related to this. If we're talking about, and like I said, I wrote so much on this thing, I don't know how legible it's going to be at this point, guys, but there's the DS. Here's R hat. And there's a whole bunch can be said, guys. Let's just talk about it. If this is for our purposes, so let's say we're finding the infinitely long wire. If that's the case, I'm going to double it. I'm going to try to just work with triangles going straight up like this. I know many of the rules that I need to know, these that have been mentioned and other ones, as we all know those rules, and we're going to use them. We're going to use whatever we need to use to get this thing done. Here's ds vector. And again, this is the magnitude of it right here. So I didn't call it a vector, but now, I'm not calling it a vector, but this is the size of it. And if you want to call it a vector, here it is. Here's the vector. It's ds long. Here it is. ds vector, here's our vector, the whole thing right here. ds vector cross r vector. You know what you're doing. Right hand rule, roll it over. ds vector cross r vector. Here's the r vector. ds vector cross r vector, bam. Right hand rule, ds vector, cross it over to r vector. ds vector, cross it over to r vector. Right into the board. This is going to be going right into the board. Okay. It's going to be doing that everywhere, guys. It's going to be doing it here as this thing's working its way. As it's going that way, it's going to go up. Yeah? Why don't you draw another triangle down here just to prove it. What about another triangle down there, you guys? What's going on? If the other triangle was on the low end, like this, and this was your r vector, and your ds is doing this. Here's your ds vector. Here's your r vector. Here's your theta. I said it was going to be a 90, here it was 120 degrees, which means this is 60 degrees. I can draw an identical triangle and make that 60 degrees down here. I don't want to draw too much here, guys, because I think it's going to get more confusing if there's too much clutter here. But I can basically take this and flip it down this way. This is 120, this is 60, and here's 120, here's 60. 120, 60, flip it down this way. There's a 60 right here. There's your 60 degree angle. Go ds cross r vector. Go ds vector. Don't want to put that on there because I didn't put it over here, but it is a vector, and we know this is r, and it's doing this. That's the r vector. Why don't you cross them? ds cross r. Wait a minute. My thumb goes into the board, just like it did over here. My thumb's always going into the board. Regardless which part of the infinitely long wire that we're talking about, if the direction of I does not change and is going straight up like this, whether it's here, and same thing here, whether it was here, going straight up. Now, regardless of, if it's going straight up like that, both semi-infinite parts of the infinitely long wire, both semi-infinitely long, both rays that are infinitely long, right, or whatever, it's not really, rays not a good way to say it. Both semi-infinitely long parts of the wire having the exact same direction and magnitude of current, I, shooting straight upward like this. When you evaluate it in both circumstances, ds cross r, boom, your thumb goes into the board. ds cross r, bam, your thumb goes into the board as well. It's going to do this in both instances. I'll tell you what, let me find 1/2 of the situation, if you allow me to say that. One part. Let me find a semi, let me cut it sort of in half, if there's such thing as half for an infinitely long wire. But let me cut it and then find out what happens. Let me cut it perpendicular to P right here. Let me kind of just in my mind cut it and find out what the total B field is right here. Whatever that B field is, it was also occurring on that part of it as well. The exact same B field was occurring on that part of it as well. So the amount of B field down here was B, because it was the exact same thing was occurring down here as occurred up there. B and B is 2B. So whatever I find here, all I got to do is double it, and I got the whole thing. Or if I just find the whole thing, I can cut it in half, find out what the semi-infinitely long one is for this special case scenario. Okay, I think the mathematics is pretty interesting when it's done, so I wanted to talk to you about it if I could. It's a lot to be said. I'm taking, sort of taking our time here with this. Let me just try to think what else I kind of want to say regarding something like this, you guys. Let's erase some of this. And like I said, a lot of the mathematical concepts used here are good for the problems that are in there, assuming that the assumptions are clearly explained and or you feel comfortable with the assumptions. Sometimes I'm not entirely comfortable with assumptions that get made. Sometimes mistakes get made as well as far as what the assumptions are that are presented. They may not be valid, but that tends to be a rare situation. Answer keys to be trusted. As anything else, as with anybody trying to teach the material, including myself, what assumptions are made and what assumptions are not made are a very important thing, and maybe some things need to be more explicitly said. At the very least, I want to show you some of the calculus that goes in to looking at that infinitely long wire and the semi-infinitely long wire to actually get it. Let's sort of talk about it, I guess you could say. We already said what's going on regarding some of this stuff. Let me you have access at least to where it's coming from, guys. The drawings and some of the assumptions related to the drawings. So you can always go back with the film and kind of look at it and double up on, look at what's been said again and kind of work at it. So there's a lot to be said here. We know from previous work and previous discussions, either with me and or with somebody else, that A vector cross B vector, in terms of like directions, the right-hand rule and stuff like that, in terms of magnitude, there's a lot that goes on. I mean, so let's, forgive me here, guys, So if we talked about the magnitude of A vector cross B vector, sometimes they just put it with two lines like that. Other places they'll put, two lines real close to each other, two lines real close to each other, get that. The magnitude is the magnitude of A times the magnitude of B times the sine of the angle between them, and everything obeys the right-hand rule. Regarding something like that, you're talking about essentially A vector cross B vector equals AB sine theta, and the vector under consideration, the result of the cross multiplication, is a vector with this magnitude that is perpendicular to each of these two vectors, A vector and B vector, in a right-handed manner. Pretty fascinating stuff. I mean, there's a number of proofs on this where it gets discussed that are really beautiful to look at. I can tell you for sure. So that's that's its own discussion. I've tried to talk about some of it and look at some of the great work of Munham and Foulis regarding some of that work and some other stuff that I've tried to look at. I've tried to present as well. I'm sure I wasn't the first person to present it. This stuff is very old. The material is beautiful that they've done to actually develop the mathematics for this stuff. We have this, we understand this, we can say a bunch of things. Let's just talk about the magnitude of it. We already figured out the way I had set up the scheme, the way we just hypothetically set up the scheme, that the vector is definitely, the cross product is going to go perpendicular to the board, into the board. You saw me do it. So, great. So we know that. We know everything's adding up. They're not going to cancel out. From either end of the semi-infinitely long, from either end of the infinitely long wire, semi-infinitely long wire and the other semi-infinitely long wire, that is, so you put them together, semi-infinitely long wire and another semi-infinitely long wire. As you put them together, they total that infinitely long wire, and in both cases, the B field goes in just one direction, the same direction in both scenarios, as we just said. So we're looking at it like this, you guys. Since we've said a lot already on that, I don't need to repeat some of the stuff that I said, but I still think I'm going to have to draw. It's a good idea to draw some things when we do some of this stuff. As far as the magnitude is concerned, you just saw what I wrote there, guys. You just saw what I wrote there. So what this right here means in terms of magnitude IDS let's try to figure out here exactly what we're going to say here. This should have been the way they drew this. I may have. This needs to be kind of looked at a little bit more, which makes perfect sense, actually. Okay, there might have been, I think, 837 here, guys. Yeah, there's a bar here, guys, so forgive me. There's, in the discussion, and this is a very big thing, actually, very important. That's our bar. So this is a unit vector when you talk about it. So that's very important. The way it was drawn, so be very careful with that. It's that R vector is that's not accurate. Actually, the way it's supposed to be is like this. So watch out. I mean, this has got to be a unit long vector. So it's not the fact that it's a unit long vector and not R vector. It's not going to contribute anything here to canceling out R squared, which makes sense. It's an inverse square law related to where it's at, you guys. So watch out with that. So that right there, be careful. Halliday and Resnick definitely corrected me on that. I have no idea why I put it like that when it should have been it should have been a unit vector right here, you guys. So that's okay. What does it mean? Well, ds vector is very small, and r hat is a unit vector, so that's not very much of an issue. If it's a unit vector is size 1. This becomes the size of ds vector times the size of ds vector times the size of r hat times the sine of the angle between them, and that's the sine of the quantity 180 minus theta equals the sine of theta. All right. Well, this right here is just ds. It's very, very small. The magnitude of r hat is 1, and this is the sine of theta. So forgive me, guys. I did the math right, but my symbols were way off. That you do not put it like that. You put a unit vector right there. So if I get a chance to talk to people in person on this as well, we'll mention that as well. So please be aware of that when we talk about it. So if that's the case, we got we got ds sine theta, and we got that this right here, and this is kind of the way we had done it, guys. So forgive the typographical error on my point. On my part, please forgive that typographical error. That's entirely my fault. Yeah, definitely it's an inverse square law. Yeah, if this would have been R vector, its magnitude plays into the situation. This would somehow have a magnitude of R present. A magnitude of R cancels with one of the magnitude of R's here, and it would just be an R on the bottom. Well, yeah, that's not an inverse square law. It's an inverse law. It's related to the inverse of R, but it's not an inverse square law. And they told us it was an inverse square law. If this would have been the magnitude of R vector, if this would have been R vector as is, just R vector, somewhere the magnitude of R would be manifested in this cross product. You would have, don't do this, and like I said, I almost did it. When you got this right here crossed, if it was something like this, let's just say it for the sake of saying it, this is the magnitude of ds times the magnitude of R. This is the magnitude of ds vector, the differential element ds vector. This is the magnitude of it, which is just ds. This right here, R vector, would pertain to the magnitude of R vector, which is R, and this is the sine of theta. It would be ds R sine theta. Well, that's a problem. Well, somewhat of a problem. Because if you were talking about the magnitude of dB, and again, we're not doing this, but just for the sake of argument, we've got mu 0 over 4 pi. You got R squared right here. Yeah, that's all well and good. If you cancel the R, if the R and the R squared cancel, if the R and the R squared cancel, you got an R on the bottom. Okay, yeah, that's the math. They told us it was an inverse square law. Where's the square if there's a cancellation there? It would not be present. So please note how I wrote that. I'll try to bring it to people's attention. I'll figure out, what's being brought to your attention right now, basically, guys. So we look at it, and this is brought to your attention. So don't look at my typographical error earlier of R vector is wrong. It should be R hat. R vector is a vector that is conceivably bigger than the unit vector, could have a very, very large magnitude, and it would eventually cancel out with the R squared right here, leaving you an R on the bottom. Well, yeah, that's the mathematics. The problem is Biot-Savart's law is an inverse square law. The inverse square law is thrown out the window. Not thrown out the window. The inverse square law is not maintained if the R and the R squared cancel with the wrong mathematics with the wrong mathematical symbol that I brought in there. If this was just a regular R vector here, the inverse square law would quote unquote be thrown out the window. Well, that's not the case. Biot-Savart's law is experimentally proven, and it is an inverse square law. If this is a unit vector, it won't do anything. Won't do anything to that. So that's very important. So I want to just kind of say that. Watch out. Just watch out. This right here, if conceivably we were going to follow that logic, we're going to a bad place. We're going to make a mistake. Don't do it. This is where it goes when we come down to here. That's what we're supposed to do. All right, and that's what we have written down there. I have all that from here on in. When you're looking at my notes here, it's on when we do that. Okay. Are you able to say anything regarding that? So that's the ds sine theta right here, you guys. Pretty fascinating stuff, really. The more you look at, the more fascinating the material is, guys. To be honest with you. I ds vector cross r hat, I ds vector cross r hat over r squared times the constant mu 0 over 4 pi. Pretty fascinating stuff. So we got this right here. Is it true that if you were looking at what we had earlier, let me just kind of put some of the mathematics on there that we can kind of look at it. So if you have, as we got this, guys, let me kind of, I'm arguing here with myself how I want to look at it. This is the length r. This is r hat. And this is r vector. R vector, the length of r vector is this entire thing. R hat is just a unit of length. This is the ds vector, however you want to say it. Here's S. Here's R. We said there's a whole bunch of ways to write it. We wrote it last time, so you can kind of go back to see there. So everything's fine here. As far as the theta is concerned, we said that the sine of theta is equal to the sine of the quantity 180 degrees minus theta. The sine of theta in terms of radians is equal to same kind of argument. Sine of theta, if we're talking about radians, is sine of theta equals the sine of the quantity pi minus theta. All right. You got something like this. What the heck's going on here, guys? Is it true if theta is this and this is 180 minus theta, or pi minus theta, capital R divided by small r will get you there. So let's see what we got here. I may have gone about it. Yeah, there it is. Okay. Here's small r. Here's capital R. So what's sine of theta? Well, the sine of theta true. We got anything else we can say related to that? Yeah, I mean, we can say this. We could say, for this right here, we could say dB is equal to mu 0 over 4 pi mu 0 I mu 0 I ds, so 4 pi r squared on the bottom. Mu 0 I ds. What's going on here? What's capital R? Capital R remains what it is. They haven't really said too much about it. This right here is the square root of s squared plus the square root of r squared. So what's going on here? I mean, there's a lot. I mean, let's say it, let me say it maybe a little differently. I don't know. A horse apiece on this sometimes, guys. I mean, you got this. You got 4 pi. You got I. You got ds. You've got, I tell you what, I mean, you can write it a whole bunch of ways, guys, right? S squared, R squared, one half. Well, we already said that R was the square root of this. So this thing is just, that's the small r on the bottom. Small r right here. Small r on the bottom is s squared plus r squared to the 1 half That's R squared. Well, 2 times a half is 1. It's just, you know where that's going to go. You know where that's going to go. What's going on here? Well, I got an idea. I mean, this is not the only idea, but I mean, this is an idea. Put that to the 1. Tell you what, call this thing right here, call it something, some variable, whatever you want to call the variable. Call this capital A, this right here, call it capital A. Capital A to the 1. And this right here is also capital A, but it's to the 2. This is on the bottom. This is on the bottom right here, so you can bring it right here. So it's capital A to the 1 times capital A to the 2. It's capital A to the 3 when you actually do it. And then the R stays on top. So what happens is you wheel and deal with some of the stuff I just wrote up there, guys. You got the R right here, and we said this was the capital A to the 1/2. This whole thing was the capital A, and you had essentially, that thing came down. You had this right here, guys. You had S squared plus R squared to the 1/2. And let's just talk about this guy. This. It was that, which is really to the 1/2 squared, and you get this. Okay. Well, that right there is just R over, this guy comes down, and you got S squared plus R squared to the 1/2 times S squared plus R squared. True, absolutely true. So, what is that? Well, didn't we say that was S squared plus R squared to the 1/2 this thing right here, that whole thing is to the 1. Nothing profound there. This thing right here to the 1/2 is being squared. Well, wait a minute. That right there is the capital A. This is another capital A. Capital A to the 1 on the bottom. This all happened on the bottom here, on the denominator. We're just doing denominator. We get a new denominator. We get a new denominator at the end of this, or at least a simplified denominator. This whole thing is capital A to the 1. This whole thing is capital A, and it's being taken to the 2. Capital A to the 2 times capital A to the 1 is capital A to the 3, which is S squared plus R squared to the 1/2 taken to the 3. Well, what is this quantity taken to the 1/2, that entire quantity taken to the 3? 3 times a half is 3/2. So at the end of the day, one half taken, this quantity to the 1/2 taken to the 3 is this thing to the 3/2. We know enough of the math and we're comfortable with it that we're okay with that. It's absolutely true. Tell you what, if I'm going to find the length of the entire infinitely long wire, we see what I can say. So we said what we said here, guys. Okay, looking pretty good. DB is looking like that. see what I can say here. Maybe I can talk about a few things that are they're very pretty fascinating stuff, I think. How would everyone feel about, we've got this right here. We haven't really done the integral yet. If we're going to do the integral from negative infinity to positive infinity, if I just multiply it by 2, if I'm going to do the integral of the infinitely long line from negative infinity to positive infinity or something of those lines, how about I just do kind of sort of half the circumstances and then double it at the end? And that's kind of what they're talking about for doing this thing. Well, I'll tell you what I'm going to do. As we keep working with this thing, let's say something. Is it true that you could put an r squared here? And what's r squared over? If you multiply by r squared over r squared, do you change what the thing is? R squared over r squared is 1. Capital R squared, and to be more specific, capital R squared over capital R squared is 1. That's what I want to do. Capital R squared over capital R squared is 1. Let me multiply it and see. Why am I doing that? We're staying with what we did earlier. Doing it a little different from the notes. It's essentially the same thing in the notes, you guys. Just a little different ordering of the whole problem. Why have I done that in the first place? What is r squared times r? Is that r cubed? True. Mu 0 over 4 pi capital R squared. I'll bring the r squared. I'll bring this r squared over there. It's a constant, no big deal. What is going on? Okay, it's believable. I said I'm only going to do half, if you allow me to say half, for an infinitely long line, and then when I'm done with it, I'm going to double it, and I'll have the whole length. I've accounted for the B field associated with the entire infinitely long wire. When I double for the semi-infinitely long wire, when I double the B field associated with the semi-infinitely long wire, I will have, when I double that, I'll have the B field associated with the infinitely long wire. Let's talk. Let's keep talking, guys. There's a lot here. Again, you've got the feature to go back here on this stuff, guys, and figure out what's going on. Let's talk. Is r cubed over s squared plus r squared to the 3 halves the same as r over the quantity s squared plus r squared to the 1/2? The whole thing taken to the 3rd. Is that true? The exponentiation of a ratio is the ratio of the exponentiations. Yeah, it's true. I've got more of a question to ask. That, the sine of 180 degrees minus theta is the same as the sine of is the same as the sine of theta. The sine of theta and the sine of 180 degrees minus theta is the same thing. The sine of theta is equal to the sine of 180 degrees minus theta. What is the sine of 180 degrees minus theta? It's the same as the sine of theta. It's opposite. It's opposite. It's opposite over hypotenuse. Here's your hypotenuse. Here's your hypotenuse. Really? Well, that's the sine. We just said it. We just said it, I mean, kind of in a roundabout way, but here it is. The sine of 180 degrees minus theta is equal to the sine of, in radians, the sine of the quantity pi minus theta. And in both instances, with the appropriate units in place, that's the same as the sine of theta. Either in degrees or in radians, depending on what you're talking about. Just be consistent with the units. Sine of theta, where theta is in radians, is the same as the sine of the quantity pi minus theta. The sine of theta in degrees is the same as sine of the quantity 180 degrees minus theta. What is the sine of theta? It's the sine of this. That's the opposite over the hypotenuse. That's capital R over this. Wait a minute. Capital R over this, you got it. Wow, that's pretty drastic. Perhaps it's easier to look. Perhaps it's somewhat easier to look. There's other ways this can be done. I mean, if we looked at something in a table of integrals, it works. But let's do this, and we can say a lot of things. Whole lot here, guys. I mean, this is important. I mean, once you got to here. So there you go. Well, let's deal with it then. I mean, we got that, and there's got to be an easy, maybe something's going on here that can help us out. So dB that can be that's written in a number of ways. Sine theta, the quantity cubed. Oftentimes, they just write it like this. Okay, so what? I mean, well, not so what. It's. I mean, there's a lot of good here. I guess. Units aren't really your green, or at least symbol. I mean, some of the non-numeric symbolism is not necessarily your green. Doesn't mean it's not true. This is all true, but for me to eventually do an integral, I'm going to integrate with respect to s. I'm going to go. I'm going to use df. I'm going to integrate with respect to s. How on earth am I going to make that something in terms of theta? Well, how does ds change? You got to look at how this thing changes. And basically you can say, okay, well, wait a minute. There is as the angle gets bigger, here's when the angle theta, there's a theta 1 right here, and there's another theta 1 right here. And this is a ds right there. Well, yeah, or a ds or a delta s. What do you think? Well, I think, again, it's easier done than said, you guys. This is really a key point here. I guess I could say to you, if this is theta 1, which ain't real big, and theta 2 is bigger, I tell you what, this is associated with that, and the other whole thing, all of that, associated with this. I got to find ds. So I guess if I could find, this, that long length, and then find this shorter length, and do a subtraction, I'd get the ds. Looks a lot like a tangent somewhere. I mean, if you look at it, I mean, you could say, I'll tell you what I'm going to do. I got to be pretty innovative about this. Let's find the length of this guy, which is, this is S1. This one right here. That's S1. And this one right here, that's S2. I'll tell you what, I got to be careful here, and I got to make sure everything's agreeing here. Do you agree that delta S, which is approximately equal to, if it's small enough, it's approximately equal to ds. Delta S is S2 minus S1. Yeah. Is it true that capital R divided by S1 is the tangent of theta 1? Tan of theta 1 is S1 over capital R. Tan of theta 2 is equal to S2 over R. Yeah, the S2 is pretty long. Yeah, it's longer. As I'm taking a walk here. Is that true? Well, let's just, again, say it. I'm sorry, I just said something I shouldn't have said. Let me reverse that, guys. It's capital, it's essentially, kind of jumping the gun here on this thing, guys. Tan theta 2 is this entire thing tan theta 2 is this entire thing here divided into R. So it's capital R divided by S2. That's tan theta 2. It's the tan of this angle, guys. This angle is 180 minus theta 2. This angle is 180 minus theta 1, and it works out fine. So don't let that scare you. We got here, for this guy, we know that capital R divided by S1. Capital R divided by S1 is tan theta 2. Capital R divided by S2. Right? So capital R divided by S2 is tan theta 2. Capital R divided by S1 is tan theta 1. Okay. Now what? let me say something. Tell me how you feel about this, guys. S2 minus S1, huh? Would everybody agree that R times S2 over R minus S1 over R, capital R in both cases? Does everybody agree? I'm not getting specific just yet. I just want you to, I want to ask you, do you believe the mathematics? Do you believe the mathematics? Yeah, I believe it. We might look at it. We believe many things here. We believe this. We believe this, and if we do believe this, and it makes sense, S2 is the long one, S1 the short one. The difference between the two is this. Is this delta S. The difference between the two. Delta S, ds, okay, I'm going to say they're approximately equal. Let's not split too many hairs. Is it true sounds good to me. R times S2 over R is S2. R times S1 over R is S1, and you got this. Yeah, sounds good to me. Can I ask another question? Here's R. Here we go again. Is S2 over R the same as 1 over R over S2? You're wondering, why is he doing this? Well, you'll see. You might not be wondering. You may have caught it. You may have caught it quite a while ago, actually. Is S2 divided by R? Is S2 divided by capital R the same as 1 over the quantity capital R divided by S2? Yeah, it flips around and you get this. Okay. Is S1 divided by capital R the same as 1 over capital R divided by S1? Is that true? Yeah, it's true. Yeah, great. Didn't we already say this? It wasn't pretty to look at. We already said that, though. We got this right here. Wait a minute. R over S. Capital R over S2 is tan theta 2. Capital R over S1 is tan theta 1. On the bottom, put tan theta 2. On the bottom here, put tan theta 1. What do we got? Well, we got delta S, which is kind of sort of the same as ds, right? We'll say it's approximately equal to it. Yeah, true. Right. Just trying to argue a little bit with myself there and what to say. Is that right here, delta 1 over tan some theta. Times R equals delta S. True. So what? Well, let's stay with it. Delta S and ds are pretty close. Any ideas? Yeah, I got one. What do you say you take on both sides of this and divide by delta theta, some change in theta? That's the same as yeah, true. What do you say you, a lot of ways to go here, guys. Let me just stay arguing with this. What do you say you take ds over d theta and multiply by d theta? Why are you going around in circles here? I mean, yeah, I got delta S again. I got delta S over d. I'm calling them d's and deltas here. Kind of interchangeable, kind of not. If I'm taking delta S over delta theta, and multiplying by delta theta, I got delta S. You're probably wondering, what is he doing? Why is he doing that? I'm going to multiply that side. I'm going to multiply by delta theta on each side. What's going on? What's going on here? Well, what's going on here is, in the limit, as delta theta gets smaller and smaller and smaller, you've got ds d theta times d theta equals r as d theta goes towards 0. This is delta 1 over tan theta over delta theta is really d 1 over tan theta, which is its own adventure. d theta here. Pretty fascinating. Great argument. Absolutely true. ds d theta times d theta is just ds. Now I'm kind of getting to where I want to go. Okay, let's see what we got here, guys. ds d theta times d theta is ds. ds d theta, ds over d theta, which they call it ds d theta just for short. ds d theta, the derivative of the s function with regards to theta, ds d theta times d theta is just ds. ds is this. Yeah, it's that. Definitely that. So how are we going to do it? Why don't we find the derivative of the 1 over tangent function? And go from there. I'm not entirely comfortable with how good the visualization is at the corner of it, guys. I think there's enough room on there. I think it's working out okay. But let me just kind of be a little careful. What are we doing? Well, I'll tell you what. Let's find the derivative. And like I said, at the end of the day, this thing just comes out to here. As it comes out like this, let's figure some stuff out. Tell you what, let's try to stay not too far on the edge here, guys. I think this should be pretty visible for you guys. I'm going to make it relatively big too. Let's find out what this thing is. This solves it. If you get to here, we're kind of where we need to be, if you get all this. So, they are asking for the derivative of this function, the 1 over tan theta function. If we're dealing with the right angles, we're never really going to have it at 0. So I guess maybe here's where the semi-infinite length of wire is, and then doubling it really works out good. Because I'm going from 90 degrees to 180 degrees. I'm going from pi over 2 radians to pi radians. And the tangent, the tangent is not going to blow up to something undefined. Or it's not going to go to 0. It's not coming to 0 on any of these. So, okay. There's a lot of arguments you can make here, guys, but we're not going to worry too much about this. The main thing is, can we get this thing done? Can we get it? Can you take this and go d theta? Does everybody agree? D of the function 1 over tan theta d theta. 1 over tan theta, well, the tan of theta is sine over cosine. 1 over the tan of theta is cosine over sine. Let's do the quotient rule. This is F, this is G. F, G. G, F prime. G, yeah, right. This is F. After we do the whole song and dance, this comes to here. Tan of theta is sine theta over cosine theta. 1 over the ratio sine theta over cosine theta is cosine theta over sine theta. Sounds good to me. Get the derivative here. We'll call the top F. Function F is the top. Function G is the bottom. G F prime is sine theta times negative sine theta. Negative sine squared theta. Minus, so G F prime is negative sine squared theta. G F prime is negative sine squared theta. F G prime is cosine squared theta. And on the bottom is G squared, that's sine squared theta. Again, I don't know how much room I got over there, guys, so let me try to bring that. Go over here. How we were playing the game here, guys. We got a negative. Guys, you got negatives all over the place. That's okay. There's a negative here, and this minus cosine squared theta is plus a negative cosine squared theta. Wait a minute. There's a negative 1 right here, and there's a negative 1 right here. Why don't you pull the negative 1 out of there? Well, let's see what that was, guys. Yeah, was that sign? Yeah. Ladies and gentlemen, you know where this ends. Sine squared theta plus cosine squared theta. Sine squared theta plus cosine squared theta is 1. 1 times negative 1 is negative 1 over d tan. Sorry. Yeah, simply this, guys. So let me just rewrite that. A lot of ways you can write it. You know, there's all these fancy terminology on it. This is key. That's key. What's going on here? What is all this then? This d of 1 over tan theta, d theta, is negative 1 over sine squared theta. That's d theta. These cancel in a sense, and you got ds. That's important. Well, here goes. At the end of the day, what we got was ds was equal to negative 1 over sine squared theta r, negative 1 over r squared theta r. Let's see here, where we were, guys. ds. Yeah, there it is. There's the ds. ds, there's a capital R. This is negative 1 over sine squared theta, and this is d theta. You just converted talking about ds in terms of d theta. That's huge. That's huge. In fact, you're going to take all this, and you're going to put it, right here. Basically, what you got here is you're going to take the ds, which is all that. You're going to put it right here. Absolutely. Absolutely. What's going on here? dB equals mu 0 over 4 pi r squared. I ds which is this, r d theta times the sine cubed of theta. I know the d theta's, have the d theta right here to be consistent. Who cares? You're doing multiplication, guys. It's all going to stay there. It's all going to stay where it needs to be. Well, wow, there's just a lot coming right at us, man. But the biggest thing that's jumping out at everybody, here's sine squared theta. Here's sine cubed theta. The rest is pretty basic stuff. dB. Oh yeah, here's an r squared right here. Here's a capital R squared. Here's a capital R. They cancel. You got mu 0 over 4 pi capital R I times sine squared theta into sine cubed theta is just sine theta. There's a negative here. Well, throw it right there, guys. Why not? Absolutely. Absolutely. And I show the argument on that in problem 88. I kind of show that argument. I didn't like some other aspects of problem 80. Some things it's not really directly related to problem number 88, but I have some extra stuff we needed to look at. The actual assumption made in problem number 88 to me was not very clearly explained. So I didn't really want to go there. I was having a hard time myself following what was going on. I'm sure it's something trivial that I'm missing. Perhaps there's an error in how it was approached to begin with. I tend to doubt that. I mean, that does happen sometimes, but I'm sure the answer key's probably on the mark. I'm just not following it too well. But this at least, and that's a totally different problem than this. This is just something, you'll find the explanation of this in problem 88. I've just figured it was something extra that needed to be talked about. This is huge, guys. I mean, you get to here. And that's about it. I mean, they're gonna, you can look at this thing and see how we're gonna play it. let me just go with it. Let's work through it. Very fascinating. I mean, just the whole process, if you ask me, guys. Let's do this. I is constant. Let's do an integral here, and let's figure out what we're doing with the integral. I'm going to find it for the whole wire, and when I find it for the whole wire, then I can just take half of it and find it for the semi-infinite wire. For the infinitely long wire, I'm about to find it by multiplying by 2. When I'm done, I got the answer for the infinitely long wire. If I just take the answer and divide it by 2, I got it for the semi-infinitely long wire. That's not really the real big thing. The big conclusion is what we just got. And I is a constant, mu 0 is a constant, 4 is a constant, pi is a constant, capital R is a constant. You know where I'm going here. To find B, at least in terms of magnitude, I'm going to go double the semi-infinitely long one. So 2 times, so I'm going to take this and then double it. Basically, I'm going to take, well, since these are all constants, I'm going to pull mu 0 I over 4 pi capital R. There's a negative here. I'm going to put a 2 in front because I'm only going to deal with half that infinitely long wire. You know what I mean by half? Not really half, but the semi-infinitely long wire. So I'm going to put a negative 2 right there. I'm going to put a 2 right here. This is a negative to begin with, a negative all this, and I'm just going to multiply by 2. Because I'm only caring about the integration from, well, what is the integration? It's pi over 2 to pi of sine theta d theta. What's that equal to? B equals negative 2 mu 0 I over 4 pi capital R. The integral of this, the integral of the sine function, is negative cosine. And that's evaluated from pi to pi over 2. Pretty important stuff. So you did the integral, guys, and you're multiplying it by 2, so, okay. B equals negative, the 2 times the negative. 2 times negative mu 0, 2 times negative mu 0 is negative 2 mu 0 over 4 pi capital R. I two mu 0 I over 4 pi capital R. The integral was negative cosine, right? You got negative cosine theta. I'm just not comfortable how well you can see it on that edge, guys. You probably see it quite well, but maybe you don't. Stay with radians. That's 90 degrees, and that's 180 degrees. Okay. It's equivalent. Pi radians is equivalent to 180 degrees. The cosine of 180 degrees is negative 1. Negative 1. The opposite of negative 1 is positive 1. For some reason here. Something happened here. There was a negative there. Somewhere I seem, this is a little lot of mathematics that's correct here. Let's just make sure we got it all correct. That's negative. Negative there. Negative of negative is positive. That's cosine. Negative 1 minus 0. No. I don't want to do that. Just want to guarantee some kind of an answer here that's going to be okay. For some reason here. Okay, I went from 0 to 2. I went a little differently, and maybe that was going to simplify it a little bit more. Let me just debate this guy. Somewhere I did something with a sign. I believe somewhere I did something with a sign that I should not have done. Let's just see where I did it. See, one absolute value in the end of this thing, so it's not going to be, that's not an issue. You can use just trying to figure out what I might have done wrong here. 0 to the power over 2. I think there's another negative that should go on in there, guys. We're going to get the right magnitude here. Just trying to figure out where the heck that is going. Somewhere I put a negative, guys, right? Don't need to be putting negatives. There's a negative there. Integral sign is negative the cosine. You would get at 0 to pi over 2. I don't want to take too much of everyone's time on this, guys. The magnitude answer that we're going to get is going to be absolutely correct. That's not the issue. For some reason, d theta gets bigger. A lot of it lies in the nature of the derivative of the tangent function. That value is, as theta gets bigger, that gets bigger. Some arguments you can make here, guys. Remember when we were drawing this thing, we wanted to find from there and then from there, and then we found the ds right here. As the angle gets bigger, the tan is smaller. Tan gets smaller, true, but the 1 over tan gets bigger. So if theta gets bigger, as theta gets bigger, that's for the r, you're going to get a bigger ds. That to be the case, let me just see here, guys, really quickly, if I could. Doing some stuff in my mind here to make sure this is straight. The sign gets smaller. So sine squared would get smaller. Right, there's something here with the integration here. This is fine in terms of the magnitude that we're seeking here. For some reason, I'm sure I am missing something. I think the best way to look at it is from pi over 2 to, let's see what. There seems to be something here to mention this. The s should be a positive number here. So it's a bit contradictory. What happens is if you're looking at the d-tan, the tan here for a particular theta, the tan here is bigger than the tan here. But the inverse tan yeah, this tan is bigger than this. The tan here is bigger than the tan associated with this one. So you've got this, and you've got the other one, which is all this. Well, with the yellow, if you're the tangent is a smaller answer than it is here. But the inverse tangent is bigger here. So when you, or not the inverse tangent, the reciprocal of the tangent is going to be a bigger answer. Yeah, well, if the reciprocal of the tangent's a bigger answer, when you take the derivative with respect to theta changing, as theta gets bigger, the inverse tangent should be a bigger number. According to this, right, as you take the derivative, there's something going on here. The magnitude of this should be more indicative of what's happening here. For you to get a positive answer with that, the sine of theta is a positive number. So I think somewhere this is a little bit of an issue. It's the magnitude is fine, but to be getting an answer like that means that the ds RD theta, you make a bigger theta, you should be getting a positive answer here, guys. This probably should be made into a positive, in which case it's not. Now we did the derivative is what it is. That's not an issue. But I'm just trying to figure out why the heck it would be doing that. The derivative of 1 over the tan of theta that'd be g f prime minus f g prime. Yeah, it's on. It works. what this means is if you're dealing with theta right here, as theta gets, here theta is bigger. Here theta is smaller. You're typically dealing with as the thetas get smaller, you got to go from pi over 2. I'm sorry, forgive me here. Let me think, guys. From 0 to pi over 2. And that'll work. Let me think. 0 to pi over 2. That's a -1. Yeah, I think the way it have to work. This works. The crazy thing. This is fine. This is actually mathematically accurate. But you got to remember, this theta right here, this theta sub 1 here is bigger than this theta sub 2 if you put it on the inside. On the outside, it's the other way around. Theta sub 1 on the inside is bigger than theta sub 2. So as you go to smaller values, it's a negative d theta. This actually would be a negative d theta. Negative d theta times a negative 1 over sine squared theta is a positive 1 over sine squared theta. If that was going to be the case, if you're dealing with it like that, this is bigger, then it gets smaller. On the other end of this, on the outside of this, this is smaller and the other one gets bigger. This other one, this right here, arguably is the 180 minus theta 2. This is 180 minus theta 1. The theta 1 is a smaller quantity than the theta 2 on the outside. But on the inside, it's different. And I guess this is constructed from 0 to pi over 2. It's a different dynamic with this, because here the thetas are bigger, but if the thetas get bigger, you got to make this a positive 1 over sine squared theta. It's pretty fascinating stuff. You're not trying to overturn calculus, but you have to use it within the context of what's going on. So if I were to do it here, all this jazz right here, it wouldn't be, I'd have to, if I'm going to stay with this as is, I would leave it, I would block that out. That would be like that as it's getting bigger. For me to get it, I'd have to block that out to have the magnitude. I need the magnitude of this. Well, the magnitude of a negative over sine squared theta is 1 over sine squared theta. So get rid of it. If you were to get rid of it, you've got this gone. You've got this gone. You do the integral. You've got this gone. Cosine of pi is -1. The opposite of -1 is 1. 1 times all this does it. Cosine of pi over 2 is 0. Then you get this. If you're talking about the direction that things are going, it tends to play some significant role. And you end up getting this for an infinitely long wire. If you would have said, hey, no, look, I want to go down here and then work my way up. There, this theta sub 2 I put here, it's a little different from what I said earlier. Put it down here, the theta sub 2 is smaller than the theta sub 1. So as you go up, that's a different dynamic. What you'd be doing there is the same exact thing. You'd be saying, okay, the way that plays out is It's true. See, I think one of the big takeaways here, even if this discussion is maybe, not the greatest regarding it, where does this go? What do you got for an answer here for the infinitely long wire? And then we can maybe come back a little bit. But, see, the thetas were big. The thetas were small, going to something bigger. But here, they're big going to something smaller, so you got to go a negative delta theta, a negative d theta times a negative 1 over sine squared theta is 1 over sine squared theta times d theta, which would be, and the other way it would play out, you'd say, and you'd have to do the same argument there because you're dealing with a bigger theta going to smaller values of theta, so you'd have to play the same game here. If you had it set up in such a way that it was same thing, pi over 2 to pi, same answer would be given. This can get messy. I mean, I wish we had more time. I wish we were in person talking about it a little bit, but that's kind of explaining what's going on. If push comes to shove, even if you got a negative at the end of this thing, what's the magnitude of a negative number? Its positive counterpart. It's going to be that as an answer. So it's a little, again, I'm not going to try to whitewash it too much. It's an invitation to a mess, but it does work. You got to look at how the 1 over sine squared theta is behaving. 1 over sine squared theta, as you get bigger values of theta, absolutely gets on the smaller side. True. So, I mean, something gets messed up with the integral, guys. At the end of the day, guys, I mean, what we got on this thing is what we just said. You're trying to find the magnitude of this thing when you do find it. And you do find, the 2 and the 4 cancel. The 2 and the 4 cancel. That's Ampere's law all over again, guys. It's consistent with Ampere's law. It certainly is. Infinitely long straight wire. That's for that one. If the thing was only, if it was just coming to one place, somehow you're finding some infinitely long straight wire. The semi-infinitely long straight wire is going to be half of this. What is half of this? Half of this, there it is. So this is the semi-infinite. Etc. And this is long straight wire. This is infinitely long. Long straight, straight wire, straight, Semi-infinite, long. All right, guys. Look, if you'd have done it, if you'd have kept playing the games and then just kind of done the regular calculus that we're used to seeing, you'd have gotten a negative number, but its magnitude would have been correct, and you could have negotiated how you're going to present that. You say, okay, well, I got a negative answer here, but the magnitude is the magnitude. I got a negative answer here, but the magnitude of the B field is the magnitude of that negative number, so make it a positive number. If you're going to use the calculus that's involved, guys, this is a decreasing function, but we already know we're getting a length, ds, that's a positive answer. If this is negative for a particular theta, in fact, it's always negative for a particular theta, how on earth, if this is negative for a particular theta, and r is a positive number, capital R is a positive number, capital R is a positive number, and this is negative for all theta. You know, I mean, you can get, we're not going to worry about, you know, the sign of 0 radians is 0. 1 over 0 squared is 1 over 0 squared. It goes to infinity. Okay, we're not going to go there. We're going to try to not use items that we're going to figure out the items we're going to use. But for all practical purposes, this is always negative. That's positive. This is always negative, and that's positive. Positive times positive is positive times negative is negative. No, ds is a positive answer. So what's going on here? Well, we found out, and I erased it, of course, but we found out the way this thing is moving, the answer is kind of geared to what goes on with the acute angles, the corresponding acute angles. And as we see, the angles keep getting smaller. So if you do a d theta, the d theta is actually a negative number. Well, that's okay, because a negative number times a negative number is going to give me a positive answer. Yeah, I know, but I better be okay with how I say it. I mean, I better do the integral from, I better possibly reverse it and just say, well, if that's the case, when I'm looking at how this plays out, to guarantee that, do the integral from pi, do the integral from pi to pi over 2 if you're gonna leave the negative on here. Because that 1 over the 1 over sine squared theta, I'm sorry, the negative 1 over sine squared theta. If you want to leave a negative 1 right here, yeah, please just reverse this. Well, pi over 2 is 0. Evaluated here, pi over, cosine pi over 2 is 0. Cosine of pi is negative 1. The opposite of negative 1 is 1. 0 minus 1, see, so if you've reversed it, the pi over 2 up here and the pi there, if you were going to walk it that way, yeah, you're guaranteed to get an angle. You're saying, what are you talking about? It doesn't follow in a sense. Well, if it's pi and it's going to pi over 2, the actual gradation as far as how it looks on the actual triangle, on the inside of the triangle, you're going from small angles to big angles. That kind of gets you out of it. And you can put, like I said, the pi over 2 up here, that's 0. The pi down here, that's negative 1. The opposite of negative 1 is 1, right? Right, okay, so the pi over 2 up here and the pi down here. Pi over 2 up here and pi down here. Pi over 2 is 0. Cosine of pi over 2 is 0. Cosine of pi is negative 1. The opposite of negative 1 is 1. Yeah. 0 minus a negative 1 is 1. 1 times, 1 times all this would work. So either way it would work on that. How are you going to play it? I mean, it's just, it gets a little on the rough side here, guys. You got this guy right here. It's going to be negative 1. The opposite of negative 1 as is 1. And it's going to work just great. If you're going to flip it this way, you got 0 minus, well, okay, negative 1. Cosine of pi is negative 1. The opposite of negative 1 is 1. 0 minus 1 is negative 1. Negative 1 times a negative 1 will give you the positive. That would get you there. That would work because you're actually going from a big angle to a small angle There's a lot here, guys. There's a lot here, but the math. This is absolutely absolutely a true story. The way it plays out is that if it plays out within. Just to emphasize that, it plays out within the scenario of, okay, that's an angle. That right there is actually a smaller angle. So it's going this way as you're doing it. If it's a smaller angle, that guarantees the negative d theta. And it works within the context of acute angles, not of the bigger angles, apparently. That's what the math shows. Okay. Anyway, the answer we get is what we get. Thank you all for your time, guys. Just again, be very aware of this. Biot-Savart law is great. Make sure that you're looking at it within this context. Please overlook my typographical error and look at it this way. This is the way it's supposed to look, and that's the way the book has it as well. All right. Thank you very much for your time.